Welcome back. In this example, we return to our previous matrix A, which was a 3 by 5 matrix. We're going to analyze A, and in this time we're going to find the column space. In order to do this, we recall that the column space of A was the span of the columns of A. Here we use the MATLAB notation, colon notation representing the columns. Because this is a 3 by 5 matrix, we know there are a total of 5 columns. And we can write the entire index set using index set notation. Here, the column space is the span of the columns. One of the most interesting properties of the column space is that we don't need all 5 columns to capture all of this information. In particular, we say that only the linearly independent columns of A produce the unique information we need in the column space. The linearly dependent columns don't add any new information. Recall from previous videos that we know that the RREF of this matrix is given by the matrix U with pivot columns 1 and 3 and non-pivot columns 2, 4, and 5. Because the pivot columns indicate the position of the linearly independent columns of A, we know that columns 1 and 3 are linearly independent. This is the first pivot column. This is what we call the second pivot column. Right? Using this structure, we see immediately columns 1 and 3 are linearly independent, which implies that the column space of A, the span of the columns, can be equivalently written as just the span of the 2 linearly independent columns. As we will see in future videos, we just call these a basis for the column space. The non-pivot columns help us determine a basis for the null space, which we covered in a previous video. Alright. We'll come back in the next video and talk more about how to find the essential elements of the column space using RREF form. Just for clarity, we'll write these vectors out individually. This was the first column, that was the third column. Alright, see you in the next video.